The first time that I do research was during my undergrad time at Peking University on a project using capillary electrophoresis to separate proteins. It was almost 20 years ago, and I still remember the instrument that I used. It was a Beckman Pace 5000. What this instrument did was like a magic to me at that time. You inject a mixture into it, press a button, and it separates proteins based on the charge to mobility ratio and tells you about each component. My very first user experience with a professional instrument transforms my understanding of analytical chemistry. It was no longer a subject dominated by tedious work of titrations, but a field of study to utilize and develop advanced instruments. During the same time, I became curious about Dr. Beckman. I searched the internet and learned some of his inspiring stories, like how he invented the pH meter to help farmers in California to test the ripeness of oranges and the acidity of lemons, and how he created the first instrument company and developed research tools, including the spectrophotometer. I also got to know and resonate with his vision of making a broad scientific impact by creating tools for others to do research, so the overall scientific community can benefit. Inspired by Dr. Beckman's story, by the end of my undergrad study, I had made up my mind to become an analytical chemist who could develop instruments. To gain the necessary skills, I went on to do a PhD in ultrafast spectroscopy and worked for several years as a postdoc on near-field microscopy. I started my independent research group at Lehigh University in late 2014. I feel very lucky that I can finally choose the research direction that I want to do, and I know that I want to develop chemical imaging instruments. I feel extremely honored when I was selected as a Beckman Young Investigator in 2018. The opportunity to formally associate with Dr. Beckman's name is precious to me and reinforces my belief in becoming an instrument builder. My BYI-funded project is to develop an infrared microscope that operates in the liquid phase with nanometer spatial resolution. Infrared light has been used for chemical analysis because functional groups have a characteristic infrared absorption band. In fact, the origin of infrared instrumentation traces back to Beckman's IR1 spectrophotometer, which was designed to analyze rubbers in the early 1940s. In the past, the spatial resolution of the infrared microscopy is always restricted by Abba's diffraction limit to several microns. The scale is too big for discoveries at the nanoscale. Many research targets, such as some bacteria and almost all viruses, have a size less than a micron. The traditional infrared microscope could not spatially resolve them. In addition, infrared imaging in the aqueous phase is known to be challenging because water strongly absorbs infrared light. On the other hand, many meaningful chemical reactions and biological processes happen in the aqueous phase. Therefore, new design principles are needed to overcome these challenges. In our research, we use an atomic force microscope, AFM, to mechanically detect the photothermal response from samples' infrared absorption. In 2017, we invented an AFM-based infrared nanoimaging method called peak force infrared microscopy. In the BYI-funded research, we combine the peak force infrared microscopy with total internal reflection geometry so that the infrared radiation could reach the sample in the fluid phase through the evanescence field from a prism without too much loss. We have built 2 generations of instruments. In our instrument, the AFM tip periodically comes into the contact and detach from the sample surface. The emission of the infrared laser pulse are synchronized with the moment when the tip sample are in contact. As a result, the photothermal expansion of the sample near the solid-liquid interface is detected by the AFM tip as a mechanical signal, which is dependent on chemical compositions of the sample. As the AFM tip scans, a chemical image based on the infrared absorption is obtained. We name the method liquid phase peak force infrared microscopy. The spatial resolution of the method is found to be about 10 nanometers, which is almost 3 orders of magnitude smaller than the diffraction limit. We have demonstrated on many representative samples, including structured polymers, proteins, biological cells, and polaritonic materials. The impact of this research is that now scientists have a method to measure the chemical distributions at a liquid-solid interface with high spatial resolution. It does not require additional extrinsic labels like super-resolution fluorescence microscopy. Heterogeneous chemical reactions can be monitored in situ with this method. It could transform how people study heterogeneous catalysis in the liquid phase by detecting chemicals on the facets of catalysts. The method can also be used to identify the locations of certain molecules during a biological process without labels. In the end, I want to say that being a Beckman Young investigator is a special honor and a privilege for me. I hope to carry out Dr. Beckman's legacy as an analytical chemist and meet the high expectation of a BYI through my future work.